back, everyone, to Once Upon a Lecture. I'm Merida, and I will be telling you about hypothesis testing. But obviously I can't do the whole lecture in my Scottish accent, so let's take a look at what we'll be talking about in this lecture today. So the first thing we'll do is talk about hypothesis testing. I know this is a new topic and we haven't covered it yet, but I do want you to be aware of the fact that hypothesis testing is going to be a recurring theme from now all the way until the end of the course. In this particular discussion of hypothesis testing, we're going to be talking about the one sample t-test as the first analysis that I'm going to introduce you to. So related to hypothesis testing, we have two different hypotheses. We have the null hypothesis and we have the alternative hypothesis. So the minimum number of groups we're always going to have for any statistical analysis is 2, because a comparison needs to be made between X and Y, between the sample and the population. So for any type of analysis we're going to do, we will always have 2 groups that we are comparing, and each group is going to have its own hypothesis. So we will always have a null hypothesis and an alternative. After we discuss the hypotheses theoretically, we're going to start talking about what are called t-values or t-scores. So you may remember this from the confidence intervals discussion that we had with Esmeralda previously. So this is the same t-value or t-score that we're going to expand on when it comes to hypothesis testing. Following that discussion, we're going to learn about the 7 steps. So the 7 steps are going to apply to any type of hypothesis testing, not only to the one sample t-test. So do yourself a favor and become very, very familiar with the 7 steps. And I promise that with practice, you'll eventually memorize them and it'll be just as easy as pie. Also, if you remember, when we talked about confidence intervals with Esmeralda, we also learned about chances of error or probability that there could be some type of error within an experiment. So we're going to elaborate on those errors in this discussion and see how specific types of errors relate to specific types of hypotheses. The last thing we're going to do is talk about determining significance and how the way that we determine significance differs if we're calculating a t-score by hand or if we're looking at output from a statistical software like SPSS. I know this is a lot to learn in one lecture, but I believe in us, and I also believe that fate lives within us. We just have to be brave enough to see it, brave enough to accept our own fate, and brave enough to understand that we will be able to master the concept of hypothesis testing. Let's get started. So in the field of inferential statistics, a researcher is often interested in 2 things. The first thing is obtaining data from samples, because we know that we can't test entire populations, and 2, to generalize those findings to the populations from which that sample came. Because it's practically impossible to collect data from entire populations, what researchers do is take multiple samples from a larger population. So that means they're not only going to take one, but depending on the size of the population, will determine how many samples they think are sufficient. So based on the data that they collect from these samples, they are then going to try to make inferences about the populations at large. So even though we're not testing the entire population, by testing samples from that population and acquiring data on the samples, we are then ultimately trying to make predictions and generalize the findings that we made from the samples to the larger population. A researcher's question typically involves analyzing differences between 2 or more groups. For example, if we compare a sample mean to a population mean, we can see if the means are the same or different. Perhaps the sample mean will be larger than the population mean, or perhaps it will be smaller. And so researchers typically have some sort of a hypothesis or a prediction or a hunch going into any type of analysis or study that they are conducting. So ultimately, this hypothesis is about whether or not the groups will differ, and if they do differ, specifically how they will differ. Will one group score higher than the other one? Will one group score lower? Etc. So a hypothesis is this prediction or educated guess that the researcher is bringing to the analysis in relation to the research question. But these hypotheses actually need to be tested. So using statistical analyses, a researcher can go from an educated guess or prediction to something that they can confirm if it is valid or not. And the way that we do that is through hypothesis testing. So testing these hypotheses allow us to determine if these differences are what we call statistically significant. While differences between groups may exist, right? One group may score higher than another group. The sample mean may be different from the population mean, but what we need to do is determine if these differences are large enough to be considered significant. Hypothesis testing can also help us determine if a particular change or result that we see in a dependent variable is actually due to some sort of experimental manipulation, to some sort of adjustment that we're doing to the independent variable, or if we're seeing these changes simply due to chance. It was a coincidence. It was a one-time thing. So hypothesis testing really helps us confirm and be sure whether our hypothesis can be proven correct or incorrect. So that brings us to the topic of the two different hypotheses we have: the null versus the alternative hypothesis. So once again, hypotheses are educated guesses, and they can take on one of two forms. The first type of hypothesis a researcher can have is the null hypothesis. The null hypothesis states that there is no difference between the groups that are being compared. In other words, the groups are equal. So if I'm comparing a sample mean to a population mean, my null hypothesis would be that there is no difference between the sample mean that I've collected from my sample and the population mean that exists. And it is typically characterized as H, which stands for hypothesis, with a subscript of 0, because null means 0. The other type of hypothesis you can have is an alternative. So the alternative hypothesis states that there is a difference between the groups, therefore the groups are not equal. And that is illustrated by H with a subscript of 1. So essentially, null hypothesis is H sub 0, alternative hypothesis is H sub 1. Null hypothesis says there's no difference between the groups. Alternative hypothesis says that there is a difference between the groups. So using hypothesis testing, we're able to identify which hypothesis is the one that the researcher should choose, right? Essentially, which is the correct answer to our research question. So in the language of statistics, the researcher needs to make one of two decisions. The decision can be either to reject the null hypothesis, meaning the null hypothesis is false and we're going to choose the alternative, or we are going to fail to reject the null hypothesis. The funny thing about statistics terminology is that the decision is always made in reference to the null. So instead of saying accepting the alternative, you have to say fail to reject the null. So one more time, the two options for a decision that you have, first is to reject the null, the second is to fail to reject the null. So how do we make this decision? Well, this decision depends on a statistical mathematical analysis that comes about when we calculate the t-score or the t-value. So let's take a look and see how t-values play a part in hypothesis testing. If you recall, when we talked about the normal distribution with Bell, I believe, we learned that we use z-scores to find where raw scores would fall on a normal distribution. So what we would do is we would take a raw score, convert it into a z-score, and then plot it on a normal distribution or a normal curve. So that's lovely for normal distributions, but we know that data that we collect in our field, in our experiences, is often not normally distributed, and therefore instead of using a normal distribution, we use a sampling distribution. So instead of using a z-score, we are going to use a t-score. The process is fairly similar as far as a conversion does need to happen, but instead of using the raw score to convert into a z-score, we are now going to be focusing on t-scores. So the formula for calculating a t-score looks like this. T is equal to the mean of the sample minus mu, the mean of the population, divided by standard error. You may recall that lowercase s represents standard deviation, and in order to calculate standard error, we need to take the standard deviation and divide by the square root of n, where n represents the number of people in our sample. If you want further information on standard error and how to calculate it, please visit our previous discussion with Esmeralda, who tells us all about standard error. So when we do hypothesis testing, we're actually going to have two different t-values. One t-value is going to be the t-value that we calculate or compute, and the other t-value is going to be called a critical t-value. And this critical value of t is going to be found in a special table called critical values of t. So essentially what we need to do is see if the t-value that we've computed, that we've calculated, is greater than or less than the t-critical value found in the chart. And critical values change depending on the number of people in the sample, as well as degrees of freedom. Degrees of freedom, may I remind you, are equal to n minus 1. So if I have 100 people in my sample size, degrees of freedom for a sample size of 100 would be 99, n minus 1. So the larger the degrees of freedom, the smaller the critical value. Essentially, they have an inverse relationship. So it's always better to have a larger sample size than it is to have a smaller sample size due to statistical power, which we will talk about shortly. But what you should know is that as sample size increases, the t-value, the t-critical value, decreases. So thinking back to hypothesis testing, right, to kind of connect the dots, the comparison of t-computed and t-critical values help us determine which decision we need to make about the null hypothesis. If t-computed, the value that we calculate, is greater than or equal to the t-critical value, then our conclusion is that there is a significant difference between the groups. In other words, the null hypothesis would be rejected and the alternative would be accepted. Conversely, if the t-computed value is less than the t-critical value, if the value that we calculate is smaller than the value in the chart, in that case, we conclude that there is no significant difference between the groups, and therefore the null would not be rejected, and it in fact would be retained. So, recap, and you will hear this 100,000 times from now until the end of the course. So I will repeat it multiple times, but since this is the first time you're hearing it, I will repeat it again right now. If t computed, the value that we calculate using the sample mean minus population mean divided by standard error, if that value is greater than the value we found for t in the critical table, then that means that there is significant differences between the groups. If the value we calculated using the formula is less than the value we found in the chart, then that means that there are no differences between the groups and the null hypothesis will not be rejected. Now that we understand the role of t-values in hypothesis testing, let's talk about the 7 steps. So you will be doing the 7 steps for any type of hypothesis testing, for any type of analysis. These steps apply to absolutely everything. So again, your best bet is to become friends with the 7 steps. Step 1 is basically simply to state the null hypothesis. Step 2 is to state the alternative hypothesis. And when we say state, it means just write a sentence about it. So the null hypothesis would be that there are no differences between group X and group Y. The alternative hypothesis would be that there is a difference between group X and group Y. Simple as that. Now, step 3 is setting an alpha error level. So if you think back to the last lecture we had about confidence intervals and error, we learned that we can never be 100% confident in our results. But we do accept 95% confidence, or for something way more important or more of a strict test, we accept 99% confidence. So if we are 95% confident, that means we are willing to accept 5% chance of error. This error value, this alpha, represents the 5% chance that our decision for hypothesis testing is going to be incorrect. So theoretically, the default value for error is always going to be 0.05, in other words, 5%. We are willing to accept a possibility of having a 5% chance of error, leaving us with a confidence of 95%. This is typically the default and should be used unless you are instructed otherwise. Step 4 is to find the t-critical value, aka set your rejection rule. When we say rejection rule, we are referring to that comparison of t-computed and t-critical. So step 4 is essentially going to that t-table and identifying what your critical t-value is. And the way that we do that is by calculating degrees of freedom, so n-1. Based on that degrees of freedom, we go to our chart and we look up the value that corresponds with that particular degree of freedom value. Once you identify this value, it is the value that you are going to use to compare to the t-computed value that we are going to calculate. So step 5 is actually going to be to compute the t-value using this formula, the sample mean minus the population mean divided by standard error. Once we do that, we are going to make a decision about the null hypothesis. So once you have your t-critical value and you have your t-computed value, we are going to compare them. If the t-computed value that we've calculated is greater than or equal to the value we found in the chart, we decide to reject the null hypothesis. If the t-computed value that we've calculated is less than the value we found in the chart, then we fail to reject the null hypothesis. So then you are left with the last step, which is to state your conclusion. Now we'll talk a little bit more in detail about what goes into a conclusion, but ultimately these are the 7 steps. State your null, state your alternative, set your alpha level to 0.05, find the critical t-value, find your computed t-value, make your decision, and then state your conclusion. So let's consider a very specific example and work these out all together. My Kingdom of Dunbroch has developed a training program to improve archery skills and administers it to 100 archery students. The average archery score in Dunbroch for these students was 517 with a standard deviation of 90. Data show that the standing average archery score for the entire kingdom has been 500. Is the increase in the sample mean due to my training program or simply to chance? In other words, we are comparing the sample mean of 517 who were in my archery training to the population mean that currently exists of 500 of those who were not in my training. So the question is, did my training actually improve archery scores, or was this difference due to coincidence or chance? So you may be thinking, well, duh, Merida, 517 is different from 500, so why do we need to test it? Well, if you recall, I mentioned that even though we do see differences in values, we need to test for those values to be statistically significant. Is the difference of 17 points large enough to be considered statistically significant? Is this difference large enough to say that my training program actually improved archery? So let's start with the 7-step process to answer this question. Step 1 is we state the null hypothesis. The null hypothesis would be that there is no significant difference in archery scores between students who received my training and those who did not. In other words, there's going to be no difference between the sample of students who took archery training and the population that did not. Step 2 is to state the alternative hypothesis. So the alternative would say that the groups are not equal. In other words, there is a significant difference in archery scores between students who took my training and those who did not. Step 3 doesn't really require anything on the researcher's part, just to kind of officially state that the alpha error level that we're willing to accept, 5% error, so you set your alpha level to 0.05. Now step 4 is to set the rejection rule. In other words, we need to find the critical t value. And as we mentioned previously, in order to do that, we need to calculate degrees of freedom. If I mentioned in the previous example that we had 100 students that participated in this archery competition, in that case, 100 would be my n, and n minus 1 would be 99. So once you have your degrees of freedom, you're going to go to your chart. In your chart, in the very first column, we need to find 99 because 99 represents our degrees of freedom. Once we found that, we need to move our finger to the right until we get to the column labeled 5% to represent the error value that corresponds with our degrees of freedom. Once we see that, we will notice that for degrees of freedom of 99, our critical value is 1.9840. So this 1.9840 is our critical t value. This is the value that we are going to be comparing to our computed t-value to determine the ultimate decision about the hypotheses. So just as a reminder, we have just completed step 4, where we found the critical value of t. Step 5 is now to compute t. So again, the formula for computing t is the sample mean minus the population mean divided by standard error. If you remember, the sample mean was 517, the population mean was 500, standard deviation was 90, and n was 100. So we're going to do 517 minus 500 divided by standard deviation 90 divided by square root of n. So in other words, 90 divided by 10 would give us 9. So if we further simplify that, we have 17 in the numerator, 9 in the denominator. 17 divided by 9 gives us a t-value of 1.89. So 1.89 is our computed t-value. Step 6 is to make a decision about the null hypothesis. So as a quick reminder, if the t computed value we've calculated, in our case is 1.89, is greater than or equal to our t critical value, we're going to reject the null. If our t computed value is less than the t critical value, then we fail to reject the null. So let's pull those values in and see what we got. One thing that I forgot to mention to you is that when we make these comparisons, we are making these comparisons in absolute value. So if for any reason your t computed value comes out negative, the sign of the value is not relevant because we're going to consider the absolute value. So the absolute value of 1.89 compared to the absolute value of 1.9840 is in fact less. Our t computed value is less than our t critical value. We can see that 1.89 is less than 1.984. So therefore our decision is going to be to fail to reject the null. If we fail to reject the null, it means we are not rejecting it, we are keeping it. So if we keep the null, then our decision is that the null in fact is true. So the most important part in the 7 steps is to write a decent conclusion. So because we failed to reject the null, our conclusion would read, the archery training did not significantly improve students' archery skills. In other words, there were no significant differences between the students who took the training for archery and those that did not. So the null hypothesis says that there are no differences. That is the decision that we went with. That is the hypothesis that we chose because our t computed value was smaller than t critical. So I'd like to bring your attention to the very last part of this conclusion statement. After I state my conclusion, right, there are no differences between the students who took archery training and those that did not, or the archery training did not improve students' archery skills, then I'm going to put a comma, after which I'm going to put the letter T because this was a one sample t-test. This is the type of analysis that we conducted. So a one sample t-test compares one sample from a population to the entire population itself. So the sample mean that we've collected is being compared to the population mean, one sample t-test. So in this case, we're going to say T In parentheses, you're going to put the degrees of freedom. In this case, we had 99. After the degrees of freedom, you're going to put an equal sign. Following the equal sign, you're going to put the t computed value. If you look up here at the top of the slide, we can see that the t computed value is 1.89. So we have t parentheses degrees of freedom of 99 is equal to the t computed value of 1.89. After that, I'm going to put a comma and I'm going to say p is greater than 0.05, which means the probability of me making an error is larger than 5%. If we rejected null and we went with the alternative and we saw that there were differences, in this case, everything would stay the same except the direction of the sign of the probability value. So if we rejected null and we did find a difference, we would still write t degrees of freedom 99 is equal to t computed of 1.89, but then we would say comma, p is less than 0.05. We would say the probability of making an error is less than 0.05. All right, so let's consider another example. Part of my training course focused on improving alertness when looking out for Mordu in the forest. Data from the kingdom has shown that a warrior's brain delay in response to a sound has been found to be 5.68 milliseconds. A random sample of 10 warriors were selected, and each one was asked to go without sleep for 24 hours before being tested for audio response latency. In other words, we were testing to see how long it took them to respond to a bare sound. After the test, the group's average latency was found to be 5.85 milliseconds with a standard deviation of 0.14. So the question is, did the lack of sleep have a significant effect on warriors' response time? So what we need to do is pull out the numbers that actually matter to us for our formulas. We know that the population mean is 5.68. We know that the sample mean is 5.85. We know that our sample size is 10, and we know that standard deviation is 0.14. So now using the 7 steps, let's do some hypothesis testing to answer this question. Step 1, state your null hypothesis. Lack of sleep has no effect on warrior response time. In other words, we're trying to see if the 10 warriors who didn't sleep for 24 hours are going to behave the same way as the warriors that didn't have a full night's sleep. Step 2 is to state the alternative hypothesis. So if the null says that lack of sleep has no effect on warrior response time, this would be the exact opposite. Lack of sleep does have an effect on warrior response time. Step 3, setting your alpha to 0.05. Step 4, we need to calculate our t critical and set our rejection rule. So remember, the thing that we need to do there is calculate degrees of freedom, which are equal to n minus 1. We were told that we had 10 warriors in our sample. 10 minus 1 gives us 9. So now we go to our chart, and in the first column, we find degrees of freedom of 9. After that, we need to slide our finger to the right to the 5% error level because our alpha was set to 5. And we find that that value is 2.2622. So 2.2622 is our critical value. So this critical value of 2.2622 is going to be compared to our t computed value, which brings us to step 5 to calculate t. Again, to compute t, we need to take the sample mean, subtract the population mean, and divide by standard error. Once we do that, we plug in the numbers 5.85 minus 5.68 divided by standard deviation of 0.14 over the square root of 10. Once we solve for that, we get a t value of 4.25. So our t computed value is 4.25. This is the value that we are going to compare to t critical. Step 6 is to make a decision about the null hypothesis. And once again, The rule applies if the absolute value of t computed is greater than or equal to t critical, we reject the null. If the absolute value of t computed is less than the absolute value of t critical, we fail to reject the null. So in this case, we compare 4.25 to 2.2622, and we can see that our t computed value is in fact greater than our t critical value. So this is the opposite of the previous example we had. So our decision is to reject the null, in other words, accept the alternative. If you remember, the alternative said that there is a difference between the groups of soldiers who were sleep deprived and those that were not. So lack of sleep did have an effect on the warrior's response time, comma, t to represent the test we did, a t-test. Open the parenthesis and put in the degrees of freedom there, which are 9. Close the parenthesis and state the t computed value. T computed value was 4.25. And because we've rejected null, p is going to be less than 0.05. All right, now that we've learned and did 2 examples for hypothesis testing, I just wanted to tell you a bit about the types of errors that we can make relative to the different decisions that we make about the hypotheses. So we know that it's possible to make a wrong decision. We are never 100% confident in our findings when it comes to experimental psychology. So ultimately, we have to be aware that there are certain errors that can occur. Just like you have 2 hypotheses and 2 decisions, you will also have 2 different types of errors. The first type of error is called alpha, and this error can occur only when you reject the null. So alpha error is related to the decision of rejecting the null. And the error here is that we said that there is a difference between the groups when in fact there may not have been. So remember, the null hypothesis says there are no differences between groups. If you reject the null hypothesis, it means you're saying that there is a difference. So this 5% chance of error that we could be making is by saying that there are differences when in fact the differences do not exist. On the other hand, the other type of error we can make is a beta error, and beta errors correspond with the decision of failing to reject the null. So in other words, if we fail to reject the null, that means that we have accepted it, we've retained it, when in fact we shouldn't have. So we are saying that there is no difference between the groups when in fact there was. So again, alpha error corresponds to rejecting the null, and beta error corresponds to failing to reject the null. Another concept that we should be aware of is statistical power. The formula for statistical power is 1 minus the beta error. Statistical power can be manipulated by setting different alpha levels. So for example, if we set our alpha level to 0.01 or 1%, that means our power is going to be higher if we're willing to accept only 1% chance of error. I told you that the default is always 5%, which typically it is, but if you wanted to increase the power of your test, you could decrease the size of the alpha error you're willing to accept. Another way to increase statistical power is to decrease error by increasing your sample size. So as sample size increases, the chances for you to make an error decreases. And logically, this makes sense. If I have a very large population and I've only sampled a small portion of it, the chances that I make a wrong decision are going to be high. But if I continue taking sample after sample after sample, and I gain a larger representation of this population as a whole, then it's less likely that I'm going to make the wrong decision when comparing the sample mean to the population mean. And lastly, the magnitude of difference and effect size can also increase power. These are things that you should just be familiar with for this particular lecture, and we will definitely drill down deeper into these later in the course. So as far as I'm concerned, I just think that it's helpful for you to know that statistical power can be increased by decreasing alpha, decreasing the amount of error we're accepting to take, and by increasing the sample size. So the larger sample you have, the smaller your error, your chances of making an error will be. And this is just a little matrix perhaps to visualize what the different errors are. So on the left-hand side, you have your decision, reject null or fail to reject null. And then across the top horizontally, you kind of have like truth or reality. So if I reject null when the null was actually true, when it shouldn't have been rejected, that's an example of type 1 error. But if I rejected the null, I said, nope, I don't want you, null, when the null was false, then that would indicate a correct decision or a correct rejection. Similarly, if I failed to reject null, which means I didn't reject it, and the null was true, that's an example of a correct decision. I shouldn't have rejected something that was true, so good job me. But if I fail to reject the null, when in fact I should have because the null was false, then that is a type 2 error. So type 1 error is alpha and type 2 error is beta. Alpha, type 1 error, can only be made if I reject null. Beta, type 2 error, can only be made if I fail to reject null. And the last thing that I wanted to share with you is the determining significance section of this lecture. So we know that when looking for significance of hypothesis tests using manual calculations, which is what we've done in this lecture, we have to compare the t computed value and the t critical value, which of course we look up in a specific table. And once again, if the t computed value is greater than the t critical value, we reject the null. If the t computed value is less than the t critical value, we fail to reject the null. So that's lovely. But once you start looking at analyses or outputs of statistical software like SPSS, for example, there is no t critical value anymore. And while there is a t computed value, that is actually not the value that we're going to use to determine significance. So what we are going to look at is the comparison of the significance value and the p-value. Again, the p-value represents the probability of making an error, which in our case is 0.05 or 5%. So essentially what we need to do is compare the significance value to the value of 0.05. If you remember, step 3 of our 7 steps was to set alpha to 0.05. This is the same thing as saying that you're willing to accept 5% chance of error. So if the significance value that you see in your output is smaller than your p-value of 0.05, you are going to reject the null and conclude that there is a difference between the groups. However, if the significance value you see in the output is larger than 0.05, than the p-value, then your decision will be to fail to reject the null and conclude that there are no differences between the groups. Let me show you an example. This is a sample of an output from SPSS of a one-sample t-test. You can see that the first thing on the left is a t, so that's your t computed value. Then you have degrees of freedom, which in this case are 19. And then is the very important value that you see, significance, and it says two-tailed. So the significance value there is 0.008. This is the value that we are going to compare to the p-value of 0.05. So here you can see that the significance value is 0.008. So you ask yourself, is 0.008 greater than or less than our p error value of 0.05? Surprisingly, we make very simple mistakes when we are comparing decimals, but please make sure that you pay attention that 0.008 has 2 zeros before the 8 and 0.05 has only 1. Therefore, it would mean that 0.008 is smaller than 0.05. If our significance value is smaller than 0.05, it means we reject the null, conclude that there is statistical significance and a difference between the groups. Let's take a look at another example. Again, here you have the t-value, degrees of freedom, and now your significance value says 0.483. So again, you ask yourself, is this significance value 0.483 greater than or less than 0.05? Because this significance value is in fact greater than 0.05, we conclude that there are no significant differences between the groups, and therefore we would fail to reject the null. So I hope this was informative for you in understanding your first step of hypothesis testing. Again, remember, we're going to do hypothesis testing multiple times throughout the rest of the course. Anytime you conduct any statistical analysis, that is an example of hypothesis testing. So we will definitely be revisiting the 7 steps. Preferably before the next lecture, you take some time to review it and familiarize yourself with the procedure. Feel free to drop some comments below if you have any questions or you need any assistance in anything I've said in this lecture. Otherwise, I will see you next time on Once Upon a Lecture.